Hello everyone. Today we will be studying the chapter on probability, focusing on the absolute fundamentals. Whether we are rolling a die, drawing a card, or flipping a coin, we are going to learn exactly how mathematicians go about measuring uncertainty. To get started, let's define exactly what we mean when we use the word probability. What is probability? At its core, it is a numerical measure of how likely an event is to occur. It quantifies uncertainty on a fixed, predictable scale. On the far left of the scale, we have 0 or 0%, which means an event absolutely cannot happen. In the middle, we have 1 half or 50%, which represents an even chance. And on the far right, we have 1 or 100%, meaning an event is completely certain to happen. So, how do we calculate where an event falls on this scale? We use one master formula. This is the core rule of theoretical probability. The formula states that the probability of an event equals the number of favorable outcomes divided by the total number of possible outcomes. This is the master formula for finding the exact mathematical chance of any given event. Before we start plugging numbers into this formula, we need to clarify two important vocabulary words that are often confused. Let's do a quick vocabulary check. Outcomes versus events. An outcome is a single specific result of an experiment. For example, rolling a 3 on a die is a single outcome. An event, however, is a collection of one or more outcomes. For example, rolling a number less than 5 is an event because it includes multiple favorable outcomes. Rolling a 1, 2, 3 or 4. With that terminology cleared up, let's look at the two different ways we can approach probability as a whole. There are two main types of probability. The first is empirical or experimental probability. This is based on actual observations and real-world experiments. It measures what did happen, calculated by taking the times an event actually occurred and dividing it by the total number of trials. The second is theoretical probability. This is based purely on expected math. It measures what should happen, calculated by taking the favorable outcomes and dividing by the total possible outcomes. Let's compare these two types side by side using a simple coin toss. Here is the coin toss in action. If we look at theoretical probability, tossing a coin once gives us a 1/2 or 0.5 chance of landing on heads. But let's look at empirical probability by actually tossing a coin 1000 times. In this experiment, the result is 455 heads and 545 tails. Our experimental probability for heads is 455 over 1000 or 0.455. The key takeaway here is that as you perform more experimental trials, your empirical probability will get closer and closer to your theoretical probability. Now let's apply our formula to the absolute limits of our 0 to 1 scale. Let's examine the extremes, impossible and sure events. An impossible event has a probability of exactly 0. For example, the probability of rolling a 7 on a standard 6-sided die is 0 out of 6, which equals 0. A sure event has a probability of exactly 1. For instance, the probability of rolling a number 6 or less on that same die is 6 out of 6, which reduces perfectly to 1. What happens when we take all the individual, guaranteed outcomes of an experiment and add them together? This brings us to elementary events. An elementary event is a single possible outcome. Imagine a bag with one yellow, one red, and one blue marble. The probability for each individual color is 1/3. A vital rule of probability is that the sum of the probabilities of all elementary events in an experiment always equals exactly 1. As you can see, 1/3 plus 1/3 plus 1/3 perfectly equals 1. Because everything must add up to 1, we can use a clever shortcut to find the probability of something not happening. These are called complementary events. The rule is that the probability of an event plus the probability of that event not happening always equals 1. Let's look at an example. If the probability of an event happening is 0.05, what is the probability of it not happening? We simply subtract 0.05 from 1, giving us a 0.95 probability that it will not happen. To put these concepts into practice, let's first map out one of the most common tools used in probability questions, a deck of cards. Here is your map for a standard deck of cards. There are 52 total cards in a deck. Half of them, 26, are red and the other 26 are black. The red cards are split into 13 hearts and 13 diamonds. The black cards are split into 13 clubs and 13 spades. Finally, there are 12 total face cards in the deck, which include the Jack, Queen, and King in each of the 4 suits. Keep this map in mind as we tackle our first practice problem. For practice 1, we want to find the probability of drawing a card that is not a heart. Step 1. Identify our total cards, which is 52. Step 2. Find the number of non-hearts. Since there are 13 hearts, we subtract 13 from 52 to get 39 non-heart cards. Step 3. Plug this into our formula. The probability is 39 over 52, which simplifies beautifully to 3/4. We can also check this using our complement rule. The probability of a heart, 1/4, plus our answer of 3/4 equals exactly 1. Great job! Now let's try evaluating some number ranges using a standard die. In practice 2, we have 2 questions. Question 1. What is the probability of getting a number greater than 4? Looking at our options 1 through 6, our favorable outcomes are only 5 and 6. That is 2 favorable outcomes out of 6 total, which simplifies to 1/3. Question 2. What is the probability of getting a number less than or equal to 4? Our favorable outcomes are 1, 2, 3, and 4. That gives us 4 out of 6, which simplifies to 2/3. For our final practice problem, let's pull everything together with a classic marble experiment. Here is practice 3. Our setup is a box containing 5 red, 8 white, and 4 green marbles, giving us a total of 17 marbles. First, the probability of drawing a red marble is 5 favorable outcomes over 17 total, which is approximately 0.29. Second, the probability of drawing a white marble is 8 over 17, or approximately 0.47. Finally, to find the probability of drawing a marble that is not green, we use our complement rule. We take 1 minus the probability of green, which is 4 over 17. 1 minus 4 over 17 gives us our final answer of 13 over 17, or approximately 0.765. To wrap up today's lesson, let's review the fundamental laws that govern all of these equations. Here are the golden rules of probability. First is the range. Probability always lives between 0 and 1. Second is the sum. The sum of all possible elementary outcomes is exactly 1. And third is the complements. The chance of an event happening plus it not happening is always 1. Master these 3 rules alongside your base formula and you will be able to solve any probability problem you encounter. Thank you for studying with me today.